All right, so again, doing another conversion of alcohol to an alkyl halide, but this time we're using PBr3 in ether. It can also be in pyridine as well. PBr3 stands for phosphorus tribromide, and we're gonna do the same style mechanism. Now, in the previous video, I used the exact same picture just to keep the, try to keep it the same throughout in the videos, so that way you can have reference points. But normally when you have an alcohol, remember the SOCl2 and PBr3 are used with primary and secondary alcohols mostly. They can be used with tertiary ones, but it's really about paying attention to what you have going on at the time. So again, that's a secondary alcohol. It was counterclockwise, which was S notation. So we know if there's stereochemistry, the mechanism for all of these would be SN2. Now, when there's not stereochemistry, you just simply replace the OH for the halogen. It makes life simpler. But when stereochemistry is given, we have to go through this. Alcohol is a bad leaving group. So again, we at the party, we like the alcohol, we ain't trying to leave. That's pretty much all that's happening. So therefore we have to make it into a good leaving group. So bad leaving group needs to become a good one. So it's gonna attack the phosphorus group and kick off a Br. Which Br? It does not matter, guys, because all of them are pretty much the exact same. Now, on the next step, and again, I try to do all of these live, so that way, if you want to, you can write out the problem beforehand, and then you can kind of follow along with me. Retention, in order to retain a lot of the information, what you have to do is pretty much practice all the time. So I just shortened the last two BRs. I condensed it like this. You're more than welcome to draw them out exactly how they are. And then remember, you have this BR minus that's off to the side. Same idea like the SOCl2, but before the pyridine and the SOCl2 stabilize this hydrogen, we're not worried about that here. So from this part, we can immediately take this BR and attack it. And it's always an attack of 180 degrees opposite of the leaving group. That's the same thing for the SOCl2. I may have said it, but not written it down. And then this will get kicked off. Now, when that does this, and again, this is the mechanism for normally when we're dealing with ether. I'll still do the mechanism just so you can see it with pyridine, but right now it's ether. So if ether is as a functional group, as a solvent, you can just attack the BR directly to the problem, giving you, again, the BR attacks opposite. Do you have to draw the hydrogen? You don't. It was an S notation, so I'm expecting it to be an R. Everything else that popped off just became HO with the PBr2. And then just to check, 1, 2, 3, counterclockwise, which is normally S, but the fourth priority is in the front, so we have to switch it to R. So that one is for when you're dealing with ether as your solvent. Now, if it's pyridine, same exact picture, just showing you the difference. So everything as far as, let's see if I could just put this down here. Yes, that would make it a little bit easier so you can see side by side. Everything is pretty much exactly the same up until this point. So you're still gonna have the oxygen that attacks the phosphorus group, kicks off the BR, and leaves you like this with the exact same thing you see here. However, now if we're using pyridine, which is a benzene ring with a nitrogen embedded, so it's a heterocyclic molecule. So just again, same idea. The ether just allowed the Br to attack. In this case, if pyridine is there, we cannot allow the Br to attack. We actually must use the nitrogen group to stabilize the oxygen. So here, with having a positive charge, it's definitely a great leaving group. Here it's unstable, so the only thing we're doing here is stabilizing it, but it's still going to be a good leaving group no matter what. So then this becomes so it's really more so you just have to keep track. So that hydrogen went to the nitrogen. Nitrogen should have 3 bonds. It has 4. That's why it has a positive charge. Then we got to here, and then again, we still have that Br minus. Now the Br minus can go through and do the SN2 dynamic. So right here is where SN2 happens. Here, SN2 was happening right here. And sometimes it's really good to really understand, and then you start to really incorporate the understanding of SN1 and SN2 while you go through the process. So again, Br, hydrogen, the only thing that's different, when this breaks off, that O will have a minus charge, and that will still be like this. And again, the pyridine is still lingering because this has a negative charge and this has a positive. This negative could grab the hydrogen and stabilize it. But again, these are just byproducts, so we're not really worried about that portion. What we're more concerned with is our final answer, and that it changed stereochemistry, which, as you can see, it's the exact same answer. So both of them are R notation because, again, that's what inversion or SN2, they go hand in hand, and that's how you explain that one. So guys, know the difference between ether and pyridine.